Hello everyone, I'm He Zhang. Today, I'm very pleased to share our work with you. The title of our research is Self-Consistent Training for Density Functional Theory Hamiltonian Prediction. This work is a collaboration with Chang Liu, Zhun Wang, Xinran Wei, Siyuan Liu, Bin Shao, Tian Liu from Microsoft AI for Science, and Nanning Zheng from Xi'an Jiaotong University. Over the past few decades, one of the most significant advancements in computational chemistry is the capability to determine the physical or chemical properties of molecular systems with computational measures. This progress has enabled us to tackle various industrial problems, such as drug discovery and material design. Technically, molecular properties reflect the interaction among electrons and atomic nuclei. Therefore, traditional methods such as density functional theory rely on solving electronic structure methods to provide various concerned properties. Recently, many machine learning methods have been proposed to predict its property directly. Notably, as the result DFT solution, Hamiltonian is a more fundamental physical quantity that can derive all relevant properties. So due to this, more and more researchers are focusing on building models to predict the Hamiltonian matrix directly, which could serve as a unified predictor, but unfortunately, its applicability is limited by the insufficient amount of labeled data. Remarkably, we found that Hamiltonian prediction has a self-consistent principle, which enables us to train the model without labels. This good property distinguishes this task from common property prediction, and the training method also presents a good example of how scientific laws can be used to compensate data scarcity. Besides its theoretical significance, self-consistent training also can offer two unique benefits. Firstly, it can improve model generalization beyond labeled data. And secondly, it can be regarded as an amortization of DFT calculation, making it more efficient than running DFT to generate labels for supervised training. And in this page, I would like to introduce some basic concepts in DFT. Generally, it describes an electron states by a set of object functions. You can roughly imagine that each object function describes the probability distribution of one electron. And we can further expand the object function into a basis set and get a coefficient vector. And expressing all object functions into the basis set, we can get a coefficient matrix, which we dubbed as C. So technically, the C matrix could represent all information of electron state. We can build the electronic energy based on it. And the ultimate goal of DFT is to solve the electron state C by minimizing the electronic energy. After some necessary mathematical derivation, this optimization problem can be simplified to the Cohen-Sum equation, in which H matrix denotes the Hamiltonian matrix, and S is the overlap matrix between object functions. Yeah. Although it seems like a generalized eigenvalue problem, we cannot obtain the exact solution since the H matrix and the C matrix are incoupled with each other. So generally, DFT employs a fixed point iteration method to solve this equation. Yeah. And this method is also called the self-consistency field iteration. When the Hamiltonian matrix between two adjustment steps are close, we think Hamiltonian have achieved self-consistency, and the resulted Hamiltonian matrix corresponding to the DFT solution. Well, recently many methods are proposed to predict the final Hamiltonian matrix with a machine learning model, and this, although they have achieved considerable achievement, they are still limited by the data scarcity, since one needs to conduct multiple expensive SF iterations to obtain a single supervised label. But in contrast, by employing self-consistent principle, we can obtain supervision signal with only one SF step cost. In detail, assume that the model prediction is an accurate DFT solution. Then it must satisfy the self-consistency condition, which means that if we conduct another SCF iteration based on the Hamiltonian prediction, the reconstructed Hamiltonian should be the same as the original one. Yeah. So therefore, we can utilize this physical law to provide a supervised signal. And we also want to highlight some key points about self-consistent loss. Firstly, it is not just a regularization term, since the corresponding loss function completely determines the DFT solution. And secondly, minimizing the gap unnecessarily derive Hamiltonian prediction towards the reconstructed Hamiltonian, since the latter may even be farther from the solution, in which case both of them are driving to the solution. And due to the same reason, we should not apply stop gradient to the latter. Here we provide some more details to implement our training schema. Firstly, considering Hamiltonia follows the rotation and translation equivalence, we need to employ SE3 equivalent graph networks to as our backbone. And in practice, we choose QSNet since it can achieve a good balance between training efficiency and accuracy. And regarding to the Hamiltonian reconstruction, it should be noted that the loss would backpropagate over an eigensolver. So we need to do some modifications to ensure a numerically stable differentiation. And we also introduce a GPU implementation of Hamiltonian construction to speed up the training. Here we want to emphasize two unique benefits of self-consistent training. Firstly, it enables a model to generalize beyond labeled data. We can easily come across molecular scenarios where the labeled data is very limited, but the molecule structures are sufficient. In such cases, we can leverage self-consistent training on unlabeled data to improve the generalization. And on the other hand, we want to point out that self-consistent training is also more efficient to improve variability than generating additional labels using DFT. This is based on the interpretation that self-consistency training is an amortization of DFT calculation. Look at this illustration. We use each cell to denote the cost of one iteration, and assume we have this budget. If we use it on DFT calculation, it can only provide signals for a few molecules. But if we take it to evaluate self-consistent training, it can provide supervised signals for more diverse molecule structures, which is very valuable for improving model generalization. And to validate the first benefit of improving generalization, we provide some empirical results here. And following the previous work, we use three kinds of evaluation metrics, which are direct Hamiltonian prediction, the derived molecule properties, and the acceleration ratio of taking the Hamiltonian prediction as DFT initialization. For a data scarce scenario, where we only have 100 Hamiltonian labels and more than 24,000 unlabeled structures. We applied the label laws on labeled data and additionally applied the self-consistent laws on unlabeled data. The results show that self-consistent training can significantly improve the performance over all evaluation metrics. The second scenario is an out-of-distribution case. Where we first pre-train the model on labeled small molecules and want to generalize the model on large molecules. Existing methods based on supervised learning often struggle for these such cases. Luckily, we can fine-tune our model with self-consistent laws on unlabeled large molecules to improve generalized performance, and the empirical results can well demonstrate our claims. Here we validate the second benefit of training efficiency by amortization. We plot accuracy cost curves for three training strategies. The first one refers to training self-consistent laws on unlabeled structures, and the second one means that we first use DFT to label unlabeled data and then conduct supervised training, and the last one refers to that means that we can use DFT to label the unlabeled data while conducting the supervised training. Yeah, and we observe that self-consistent training converges rapidly, achieving a low prediction error with a cheap cost, but the extended label strategy keeps a plateau at first. It is only after the DFT labeling process that the prediction error starts to drop. The extended label online strategy indeed exhibits better than the former by amortizing the label cost over the cost of training, but it is still not as efficient as self-consistent training. To further study the amortization effect, we reproduce the results by representing the cost with effective SCF iterations and observe the same conclusions. The results on the out-of-distribution scenario also show a similar trend. Yeah, and we also notice that given sufficient computational budget, supervised training can lead to better performance than self-consistent training on direct Hamiltonian prediction. Despite of this, we find that self-consistent training can still give better derived molecule properties, indicating its potential in real applications. And the self-consistent training is also a way to directly accelerate DFT calculation on lots of molecular structures by leveraging its amortization effect. We observe that self-consistent training indeed requires lower computational cost than DFT to reach the same level of electronic energy accuracy, demonstrating its practical benefits of amortization. Finally, we want to show self-consistent training can significantly extending applicable scale of current Hamiltonian prediction models. In this case, we first train the model on all available QM9 molecules, and then fine-tune the self-consistent laws on unlabeled but larger molecules, and finally test on the same larger molecules. Compared to the zero-shot generalization, self-consistent training can largely improve the prediction performance by 1 or 2 orders. Another popular paradigm for molecular property prediction is to predict each property with a specific model in an end-to-end manner. However, these models cannot self-improve when generalized to OOD case. Yeah. So, but as shown in this table, self-consistent training can offer a promising improvement over end-to-end predictors for out-of-distribution property prediction. And more importantly, in a label-free manner. I think this concludes my presentation. Thanks for your attention. For any further questions and discussions, you can contact us at the following addresses. Thank you.